It's the Financial Times AI Summit in London. The year is 2024. The air is thick with anticipation. The audience a constellation of the most powerful CEOs, investors, and engineers in the world. And standing on the stage is the undisputed king of modern computing, Jensen Huang, the CEO of Nvidia. For the last decade, Huang has reigned supreme. His GPUs are not just hardware. They are the fundamental oil, the necessary infrastructure of the entire global AI revolution. If you want to train an LLM, if you want to push the boundaries of machine learning, you must buy his chips. Period. The market has priced Nvidia's monopoly perfectly, catapulting the company into the exclusive club of trillion-dollar valuations. So when Huang speaks, the tech world listens. But what he said that day wasn't a boast about new products or market share. It was a declaration so unsettling, so profound, that it instantly sent a shockwave through the Silicon Valley establishment. He warned them. He warned us. Huang declared with chilling certainty that China is not trying to catch up in the AI race. They are positioned to dominate it, not hypothetically, but inevitably. Think about the weight of that statement. This is the man who built the empire on GPUs, essentially admitting that the very foundation of his trillion-dollar domain, the digital architecture we all rely upon, is approaching a fundamental physical limit. The US strategy, as we all know, has been a policy of restriction. Export controls designed to choke China's access to the most advanced American GPUs, particularly the high-end H100s, crippling their ability to train gargantuan models. The idea was simple: throttle their compute power, slow their innovation. But Huang's warning implied a terrifying reality. The US is fighting yesterday's war with yesterday's weapons. While Washington focused on restricting access to the digital future, Beijing was busy resurrecting and perfecting a century-old computing concept, technological path the West abandoned decades ago, as nothing more than a historical footnote. This isn't just about faster chips. This is about a philosophical shift in computing itself. And if Huang is right, the AI empire built on binary code, and digital processing is about to be challenged by the return of a forgotten ghost, the world of analog computing. To understand the revolution happening now, we have to travel backward, back before the age of the transistor, back before the reign of zeros and ones. We have to go back to the 1930s, 40s, and 50s, when engineers were truly exploring the wild frontier of calculation. In those days, before digital computing became the overwhelming paradigm, the primary competitor was the analog machine. Digital computers operate by manipulating discrete, binary values, 0, off, or 1. Analog computers, however, operate using continuous physical quantities: voltage, current, resistance, or even mechanical rotation. Imagine a light dimmer switch versus a standard light switch. A standard switch is digital. It's either on 1 or off 0. A dimmer switch is analog. It can represent an infinite spectrum of values between off and maximum brightness. Early analog machines were incredible in their time. They were used to solve complex differential equations that were crucial for artillery targeting, aircraft design, and early space travel modeling. They could, in theory, perform parallel calculations instantly because the processing was happening dynamically in the flow of the electrical signal itself. But they failed, spectacularly. Why did we cast them into the technological dustbin? Accuracy. Analog systems are inherently susceptible to noise and drift. Heat, electromagnetic interference, or even slight imperfections in the wiring would cause the output to shift unpredictably. The dimmer switch might be set at 73% brightness, but due to temperature variations, it might drift slightly to 74% or 72.5%. For critical calculations, that imprecision was fatal. Digital systems, by contrast, are self-correcting. A signal is either a 1 or a 0, making the computation robust and replicable. For decades, the consensus held firm. Analog technology was a quaint, historical curiosity incapable of the precision required for modern, complex tasks. We all agreed that digital was the destination. But now, in 2025, Chinese researchers didn't just revisit this forgotten path. They paved it. They achieved something the scientific community once deemed impossible: analog computing with a precision that not only rivals, but in specific, crucial tasks, actually surpasses the steadfast accuracy of digital systems. This wasn't just an incremental improvement. This was the resurrection of a dead concept. giving it a level of precision that fundamentally rewrites the history books and, more importantly, the future roadmap of AI. The key to understanding China's breakthrough lies in eliminating the single greatest weakness of modern digital architecture, the von Neumann bottleneck. What is this bottleneck? Every time you ask your digital computer, whether it's a smartphone or an Nvidia server GPU, to perform a calculation, the data must travel. Data is stored in one location, memory, and the computation happens in a separate location, the processor. It's like a massive corporate headquarters where every time the CEO needs to sign a document, the entire file has to be physically trucked across the city, signed, and then trucked back. This constant shuttling of zeros and ones between memory and processor burns time, energy, and creates a traffic jam. As AI models explode in size, this data transfer has become the dominant limiting factor, overshadowing the speed of the processor itself. Enter the brilliant disruptive innovation from researchers at Peking University, an analog architecture based on Resistive Random-Access Memory, RRAM. This is the central magic trick. Instead of separating storage and processing, our RRAM allows for in-memory computing. They store and process the information in the exact same physical location. The data doesn't travel. The computation happens where the data lives. How do they achieve this? In a standard digital chip, a memory cell, a transistor or capacitor, represents a single bit, 0 or 1. In the RRAM analog system, each memory cell is not a switch but a rheostat, a variable resistor. By precisely controlling the electrical resistance within the material, the cell doesn't just store a 0 or a 1. It can represent hundreds, even thousands of distinct resistance levels. Think back to the light dimmer analogy. Instead of just on or off, this new analog chip can hold a massive spectrum of nuanced values simultaneously. Why is this revolutionary for AI? AI, at its core, is just massive matrix multiplication. It's millions of weighted calculations happening simultaneously. In a digital system, you perform each calculation sequentially or semi-parallelly, relying on high clock speeds and massive bus widths. In the RRAM analog system, the matrix multiplication happens instantaneously as the current passes through the network of variable resistors. The resistance levels are the weights, and the physical flow of current is the calculation. It's not transmitting zeros and ones. It's measuring a continuous physical reaction. This enables a level of intrinsic massive parallelism that no traditional digital architecture can hope to match. And here is the crucial element that validates Huang's fear. The Peking team demonstrated unprecedented precision. They stabilized the resistance levels and engineered the RRAM cells to overcome the historical demons of noise and drift. They proved that analog computing doesn't have to be sloppy. It can be exquisitely accurate, setting a new global benchmark for the technology. The proof is always in the performance metrics. When the Peking University team moved their architecture from the theoretical whiteboard to actual silicon, the results were not just impressive, they were staggering. To benchmark their invention, they targeted the foundational tasks of modern technology, solving complex matrix equations. These equations are the engine block of literally everything that matters today: AI training, scientific modeling, like weather or molecular folding, advanced signal processing, like radar and imaging. The comparison was direct and brutal. They pitted their new analog chip against Nvidia's most advanced flagship GPUs, the systems that currently command market dominance and astronomical prices. The data came back confirming the magnitude of the paradigm shift. 1. Throughput. Their analog chip delivered throughput, the sheer volume of calculation processed over time, thousands of times higher than Nvidia's best digital architecture for the specific task of matrix manipulation. This isn't a 50% improvement. It's an order of magnitude leap. 2. Power efficiency. Because the data isn't constantly being moved and processed using inefficient digital switches, the analog chip consumed only a fraction of the power required by the GPU. In a world where data centers are consuming electricity like small nations, this efficiency advantage is a strategic weapon. 3. Accuracy. Crucially, they achieved accuracy levels that were comparable, and in some stress tests, demonstrably better than the digital gold standard. The noise problem, the historical failure point of analog, was effectively solved. Now pause and consider the most critical aspect of this development: scalability. In the world of breakthrough research, there is an enormous chasm between a lab-only prototype and a commercially viable product. Many amazing ideas die because they can't transition from a pristine, clean room environment to mass production. The Chinese researchers overcame this hurdle. Their analog chips were manufactured using practical, scalable industrial processes that are already accessible within their domestic supply chain. This wasn't a physics curiosity. This was a blueprint for a new industrial standard. This means that while the West is spending billions debating the future of next-generation digital lithography, like ASMLs, extreme ultraviolet machines, China is sidestepping the entire manufacturing race by focusing on a fundamentally different and currently superior computing architecture that is easier and cheaper to produce. It's like watching two racing teams. One is relentlessly refining its gasoline engine, making it slightly faster, slightly more efficient, hitting the absolute limits of mechanical physics. The other team, however, has switched to an entirely new propulsion system, like magnetic levitation, achieving speeds and efficiencies the gasoline team simply cannot fathom, regardless of how refined their engine is. This technological triumph cannot be separated from the geopolitical context that created it. This entire narrative is a profound case study in unintended consequences, the boomerang effect of sanctions. The official strategy of the United States was clear: weaponized technological dependency. By restricting China's access to advanced American GPUs and the critical tools needed to fabricate them, the US aimed to hobble their AI ambitions and maintain Western technological supremacy. The theory was sound. AI is built on compute, compute is built on GPUs, and GPUs are an American monopoly. The reality, however, played out precisely as Jensen Huang had warned it would. Instead of slowing China down, the sanctions acted as an enormous, unavoidable geopolitical stimulus package for domestic innovation. The restrictions didn't eliminate the desire for advanced computing. They elevated it to a national security imperative. Chinese companies, suddenly faced with an existential threat to their supply chains, poured immense resources, both public and private, into deeper research, unconventional technological directions, and a fervent pursuit of full independence. We saw this playbook run years ago with Huawei. When they were cut off from American chips and Google services, they didn't collapse. They doubled down on their domestic chipset design, Kirin, and their own operating system, Harmony OS, creating a parallel, fully independent technological ecosystem. This analog breakthrough is Huawei 2.0, but on a much grander scale. It demonstrates a national resolve that views dependence as unacceptable vulnerability. When you block the primary route, advanced digital chips, you force the target to find a completely new parallel road. In this case, that alternative road was the forgotten path of analog computing. The irony is palpable. America tried to cut off the supply of the best digital chips, and in doing so, incentivized China to develop a technology that is proving to be fundamentally better than digital altogether. The sanctions intended to stall progress ended up accelerating a paradigm shift, proving that technological blockade is often the most powerful fuel for radical domestic innovation. So where does this new, ultra-fast, hyper-efficient analog capability go next? It's not just about bigger data centers. It's about enabling future industries that are currently constrained by power and latency. These high-precision analog chips unlock capabilities crucial for three major technological theaters. A. The 6G network infrastructure. We are all discussing the rollout of 5G, but the global race towards 6G is already underway. 6G promises a true fusion of the physical and digital world, requiring data processing speeds that are magnitudes faster than today. For 6G to function, especially for complex tasks like instantaneous beamforming, holographic communication, or processing massive IoT data streams, you need real-time, ultra-low latency signal processing. Digital chips often struggle with the raw, continuous nature of high-frequency radio signals. Analog chips, processing continuous electrical signals by their very nature, are perfectly suited for this task. They can handle the immense, real-time workload of a 6G environment with unrivaled speed and minimal heat generation. B. Democratizing AI training. Currently, training the largest, most sophisticated AI models, like GPT-4 or new cutting-edge systems, requires massive clusters of $40,000 plus. Nvidia GPUs housed in energy-intensive data centers. This centralization puts the power of AI innovation in the hands of only a few well-funded organizations. Analog chips drastically lower the barrier to entry. If you can achieve high throughput with a fraction of the power cost, more researchers, smaller startups, and academic institutions in China can afford to train their own large models. This decentralizes and accelerates the domestic innovation cycle. C. Ultra-efficient. Computing at the edge, perhaps the most transformative application is pushing complex AI out of the cloud and onto the edge, that is, directly onto consumer devices, phones, autonomous vehicles, wearables, and drones. Today, when you use AI on your phone like sophisticated image editing or real-time language translation, the most complex computations are usually shipped up to the cloud, processed on giant servers, and then the result is sent back down. This takes time, requires constant connectivity, and uses a lot of energy. Analog chips, requiring minimal power, enable a new reality: AI systems that learn and process complex information directly on the device. Imagine a drone that processes video in real time, making milliseconds critical navigation decisions without a signal delay. Or a phone running a massive language model entirely locally, offering instant, private responses. Companies like Chip.im, already active in the Chinese market, are showcasing how rapidly these alternative architectures can move from the lab into commercial applications. This isn't a slow theoretical crawl. It's a sprint toward real-world deployment. The entire AI ecosystem is about to shift from cloud-centric to edge-centric, and China has achieved the technological key to unlock it. While throughput and latency are crucial metrics, the true long-term battleground for global AI dominance isn't just compute speed, it is the energy equation. The world is rapidly approaching an energy crisis driven by AI. Every new data center, every advanced LLM training run, adds astronomical strain to the electrical grid. The sheer power required to sustain the current digital AI infrastructure is terrifying. Estimates suggest that AI data centers could soon consume more electricity than entire mid-sized countries. In the United States, this massive power demand translates directly into soaring operational costs. Energy is expensive, and data centers must compete fiercely for limited grid capacity. This financial constraint acts as a natural brake on the rate of AI model expansion. China, however, operates with a different strategic model. The Chinese state provides large energy subsidies for key technological initiatives and, critically, builds infrastructure specifically optimized for next-generation computing. They can commission power plants and transmission lines explicitly to feed massive AI development hubs. Now layer the advantage of analog computing onto this pre-existing strategic infrastructure. Analog chips offer extreme efficiency. They perform calculations with an order of magnitude less electricity. When combined with China's lower-cost power ecosystem, this creates an exponential strategic advantage. They can train models that are 1. Bigger, because the operational cost ceiling is lower. 2. Faster, due to the inherent parallelism of the analog design. 3. Cheaper, eliminating the dependency on expensive, power-hungry foreign Nvidia hardware. This efficiency advantage fundamentally alters the economic calculus of AI development. If you can train a massive model for 1/10 the power cost of your competitor, you can afford to iterate faster, experiment more broadly, and scale larger. The energy advantage isn't a footnote. It is the silent strategic multiplier that ensures the inevitable dominance Jensen Huang warned about. China is creating an environment where computational speed and scale are no longer limited by the constraints of high-cost, power-intensive Western hardware. The emergence of the analog powerhouse reveals something deeper than just a hardware contest, a profound philosophical divide in how the world approaches technological progress. In the West, tech giants Intel, AMD, and Nvidia are masters of refinement. Their strategy is rooted in incremental yet monumental improvement of the existing digital paradigm. This adherence to Moore's law, while historically successful, is encountering harsh physical limitations. We are bumping against the constraints of quantum physics. The Western approach is powerful but conservative, refine the known. In contrast, China is aggressively pushing into radical, next-generation computing methods that fundamentally abandon the digital dogma. We are seeing major investment in analog systems, but also in photonic computing using light instead of electrons, and various hybrid systems that merge these approaches. The Chinese approach is disruptive and high risk, but potentially high reward: reinvent the foundation. While the West is perfecting the execution of a 20th century concept, digital switching, China is betting on architectures that belong to the 22nd century. The gap is widening because the foundational assumptions are different. For decades, the global standard was that the most powerful computing required the most precise, complex, and expensive manufacturing technology, like the aforementioned ASML machines. This gave the West and its allies, TSMC in Taiwan, a chokehold on global computation. The year 2025 may be remembered as the moment when China proved that computational supremacy does not require the digital paradigm or the most advanced Western manufacturing tools. By mastering high-precision analog, they bypassed the entire technological dependency stack. This is a moment of profound realization. The foundations that shape the modern world, digital logic and binary code, are no longer the undisputed pinnacle of mathematical processing. An alternative paradigm, one deemed obsolete for 3 generations, has returned and demonstrably is beginning to outperform the foundations we staked our entire future upon. Let us be clear, GPUs won't disappear tomorrow. They remain fantastic general-purpose parallel processors for many tasks. But their reign as the undisputed, irreplaceable core of all advanced AI computation is definitively ending. The future belongs not just to speed, but to efficiency. It belongs to architectures that can handle massive, complex mathematical workloads, the bedrock of deep learning with vastly reduced power consumption, and without the inherent latency constraints of shuttling data. The analog breakthrough is more than just a technological win, it's a geopolitical escape route. It bypasses the entire Western supply chain. Think about the components of Western digital dominance. 1 US GPU giants. Nvidia, AMD. Analog chips provide superior throughput for core AI tasks, offering a domestic alternative. 2 TSMC Korean foundries. The complexity and precision needed for nanoscale digital fabrication are eliminated, as RRAM analog architecture is easier to manufacture domestically. Sun ASML, Netherlands. The reliance on extreme ultraviolet lithography, the most strategic piece of machinery in the world, is diminished, as the breakthrough doesn't require these state-of-the-art node sizes to be effective. In one decisive, unconventional technological leap, China has diversified its compute risk and insulated its core AI strategy from foreign political maneuvering. What can we, the viewers and participants in this rapidly evolving world, take away from this monumental shift? The lessons extend far beyond silicon and geopolitics. The West presumed that the digital path was the only path to high-level computation. This arrogance created a blind spot: the forgotten analog path. In our own lives and careers, how often do we operate under the presumption that the current, dominant way of doing things is the only way? When solving problems in your business, your relationships, or your health, are you stubbornly refining a method that is nearing its limit? Or are you brave enough to look at the forgotten solutions that history or common consensus prematurely discarded? The US sanctions were meant to crush Chinese progress. Instead, they forced a radical, transformative innovation that likely would not have happened if easy access to Nvidia chips had continued. Necessity truly is the mother of invention. When you face an insurmountable roadblock in your life, a financial constraint, a career setback, a sudden market shift, do you see it as a terminal defeat, or as a powerful, non-negotiable directive to find a completely new parallel path? True innovation often starts where comfortable options end. In the AI race, the Chinese breakthrough wasn't just about raw speed. It was about efficiency: less power, less cost, more output. In a resource-constrained world, efficiency is leverage. When you approach your own resources, your time, your attention, your energy, are you focused on simply increasing your input, working more hours? Or are you focusing on maximizing the efficiency of your output, working smarter, cutting waste, focusing on high-leverage activities? The quiet power of efficiency will always outlast the brute force of wastefulness. The analog shockwave reminds us that in the world of technology, and indeed in the architecture of our own lives, every structure we build is merely temporary. When a foundation nears its limit, the truly powerful move is not to cling to the past, but to seek a radical, efficient, and resilient new beginning. This is the age of paradigm shifts. The world we thought we knew, the world defined by the binary logic of O South and 1 South, is already yielding to a new era of continuous, analog, and hyper-efficient computing. We have witnessed the king of silicon admit the vulnerability of his own kingdom. The question is, are we ready for the world that will be built on the ruins of that old paradigm? What forgotten technology or abandoned method in your own industry or life do you think is ripe for a high-precision, disruptive comeback? Let me know in the comments below. Thank you for tuning in. I hope this analysis inspires you to look past the obvious and search for those powerful, unconventional solutions. I wish you good health, and until the next technological frontier, make sure you hit that subscribe button and ring the notification bell so you don't miss our deep dives into the future.